Excellent. So this is work that we've done in collaboration with Matt Reeves and Paulette Ford at Rocky Mountain Research Station. Matt's based out of Missoula and Paulette's in Albuquerque. And we were really interested in looking at climate change and rangelands and developing an approach to help land managers make decisions about activities such as grazing management and understand the possible consequences of their decisions given the face of a lot of uncertainty. And I'll just start out the presentation with a caveat that the focus of our work so far has been on the development of the approach rather than on the results themselves. So the results that I'm kind of going to be showing are more kind of to illustrate, the kinds of questions that you can look at. But there still needs to be a lot of work with some of the input data that we're using to help, improve the confidence in the results that we're getting. So when we look at rangelands, there's a lot of drivers of change in vegetation communities. And here I show, some examples of them. So we have invasive species like Catherine's talk on buffalo grass. We've got natural disturbances. We've got, human activities such as grazing, and then we've got, climate, and these are often interacting with each other. And there is, if you look at any one location in space or time, there's a lot of uncertainty about when these kinds of things are going to be happening. And I like to think about that DICE exercise that we do in the intro course. As we spread out to a larger area, our predictive power, gets a little better. But there's still questions about the kinds of future scenarios that we can consider. And despite all that uncertainty, we still need to make some kinds of, managers, for the reasons I think that Brian stated and that, Catherine's talk showed, that managers still need to somehow have projections that represent the stories, that the scenarios that they want to consider. So often when we do these kinds of analyses, uncertainties get ignored, and there's a number of reasons why uncertainties get ignored, but it's really hard to try to incorporate uncertainty into the models. And I think it's with the software tools and the way they're developing, it's getting a little bit easier, but there's still, some barriers to that. Having said that, if you ignore uncertainty, there's going to be some potential pitfalls. And, I like this slide. This is a slide I got from Colin, but it kind of illustrates the problem with, well, there's a lot of uncertainty. Let's just move forward with the way we've been doing things, or let's assume that things are going to be increasing or decreasing. When you kind of assume an average projection to base your decision on, and you run into an extreme situation that you didn't consider, you could run into some deep trouble. So I think this quote, again, borrowed from one of Colin's presentations, but I think it reflects well on some of the topics that Brian talked about, is that we can't really, our ability to quote unquote predict the future is not going to necessarily be improving, but what we can focus is try to think of a range of alternative futures and understand, well, what are some decisions that would do well under a wide range of conditions? And so I think that's what I'm going to try to illustrate with the approach. If we're not focusing on a single possible future, but a wide range of possible futures in terms of landscape dynamics, can we have a general type of approach to inform range management decisions in the face of, in this case, changing climate? And to illustrate this, I'm going to look at a study area that we worked in New Mexico. And at first, again, because this is a preliminary project, we've kind of developed this general approach for a very small study area. It's 22,000 acres. And we actually use models that are publicly available for this area from the ILAP project. So people like Josh and Max might be familiar with these models. These are sort of non-forested ecosystem models. And the reason we chose to use these models, again, was because we're generally interested in developing an approach. There's a lot of effort that already has gone into developing models for these areas, and we didn't feel like we had the resources nor necessarily the need to try to reinvent the wheel and come to this area and develop brand new models. So how can we work with existing models for this particular area? And so here's zoomed into that 20,000 acre plus study area. And what I'm showing here is a map of potential vegetation types from the ILAP project. So there's about 18 different potential vegetation types that were mapped by ILAP. Now the ILAP project stands for the Integrated Landscape Assessment Project, and it was I'm not going to say a lot about it, but it was a big project in Region 3 and Region 6 to develop models to help guide land management decisions. And if you want to know more, probably there's two really good people to talk to here, mainly Josh, actually, because he was very, very, very involved in the development of those models. But for each of these potential vegetation types, there's actually both kind of a published document that describes the models, as well as you can actually download the models. Now, the models are for an older version of the software, they're for PATH, but you can download the models and bring them into SDSIM, which is what we did. And then we identified what we thought were some key uncertainties in these models with respect to the questions that we were interested in. So one of the uncertainties that there was in these models, so these models actually have implemented in them grazing transitions, but there's not much in the documentation specifying, what are the grazing intensities that drive these transitions from one vegetation state to another? How frequently do you have to get grazed, for how many years? That wasn't really specified. There's also transitions in these models that are with respect to the drought transition. So when a drought occurs, you will transition from one vegetation phase or state to another, but there's no real description about what does drought mean, like how low does precipitation or productivity have to be, how long does it have to last. So again, that seemed to be a key uncertainty in those models. We also have uncertainty about this particular study area in terms of future climate and how it will influence productivity. And I had a nice conversation with Dan yesterday, sitting in the back. Sounds like these guys are doing potentially some relevant work to try to create projections of future productivity. I know Ben's been doing some similar work on that. So there are potentially some tools for us to use productivity projections to bring into these kinds of models. And there was also uncertainty about current landscape conditions. So we had that map that I showed of the potential vegetation types, but we didn't actually have maps of the state classes within the models. We only have frequency distributions of how much of each state class there is in the potential vegetation types. And there's uncertainty about how much grazing will be applied to these areas in the future. So for this presentation, I'm going to focus on the uncertainty around the frequency of drought and what are the levels of productivity that would be low enough that we would characterize them as drought in terms of driving vegetation transitions. Uncertainty about the future climate, both in terms of the productivity and drought frequency, and uncertainty about how much grazing utilization could be sustained on this particular study area. Okay, so here's an example of one of the models. They're kind of somewhere in between the models that we've worked with in the course and levels of complexity and the models that Louis showed during his talk. And there's a bit of a structure. The models are well organized, so there's kind of a structure to them. There is, they're described in terms of dominant types or life forms of vegetation, and as well as their seral stage. So here's another example, and again, we have the different life forms of vegetation, including annual grasses and exotics, and then we have seral stages. And the last box, on the right tends to be a shrub-based class. These are early seral stages. And so over the next few slides, I'm going to talk a little bit about the drought, how we looked at the uncertainty in drought, right? So in this particular example model, which is one of the most dominant vegetation types in the study area that we were looking at, there's drought transitions that are usually driving change towards ruderal grasses and annual grasses, and also towards mesquite invasion. So we had a time series of productivity for this area, and we're trying to relate that to drought. And again, in the documentation, all it said was those drought transitions that I showed in the model, they happen when there's a decrease in annual precipitation to elicit a change. But they didn't really say, how low does precipitation have to be? And so when productivity gets that low that you start to see those drought transitions, or does it have to be this low? So we have some uncertainty around this threshold. And in the future, looking out what we use for productivity, we used again, and this is where we could swap in other methods for projecting productivity. In this example, we used MC2. Matt had easily available access to MC2 projections of productivity for this study area, and we'd like to try different approaches. But we had 19 different GCMs and 2 RCPs for productivity projections. And you can see there's a huge amount of variation among each of those individual projections. And again, we have uncertainty about at what point do we start to see these transitions. So we structured our analysis in this way. We had one sort of scenario in which we would start to see transitions, the probability of drought transitions to start to increase from 0 to 1 as your productivity dropped below 300, and it was 0 by the time, or the probability of drought was 1 by the time you got to 200 pounds per acre of productivity. And then we had another scenario to bracket that where we would expect, even a worst case, the productivity would only have to be as low as 400 pounds per acre, and you would already start to see some of those drought transitions. So what does that mean when we look at the frequency of drought? Well, here's just under the current climate variability, 2 scenarios. So if we have that lower threshold of productivity, we wouldn't see any drought at all. None of those drought transitions occurring under the current climate. And if we have that higher drought threshold, then we start to see up to about 10% of the landscape with relatively low frequency undergoing those drought transitions. Now looking forward with different climate scenarios, so if we take kind of out of those 38 possible projections of productivity, if we take kind of the best case, it looks, note the difference in scale. So even under the best case with those particular projections, we're seeing more of the landscape experiencing drought, perhaps at a similar frequency. And then the worst case scenario, so this is the scenario that had the most drought. Again, the magnitude is similar to the best case, but a much higher frequency of occurrence of those drought events occurring on the landscape. And again, by drought events is when we start to see those vegetation transitions undergoing drought. And so here's, one of the metrics that we wanted to look at was the composition of vegetation under those two, first of all, current climate, those 2 thresholds. So what does the uncertainty mean in the drought threshold with respect to how we might see vegetation response? And note the most dominant vegetation types are this sparse grass, so about 40% of the landscape, and this ruderal grass, and this perennial grass. And so we see that if we change the drought threshold to make it a higher threshold where we start to see drought more frequently, then we expect to see less perennial grass, more annual grass, more ruderal grass. Now, bringing in those 2 extremes, so the green line is kind of the best scenario under the MC2 projections, so the GCM and RCP that had the least frequent drought, and the purple is the one with the most frequent drought. And so we see really big increases in the sparse grass and decreases in the perennial grass, which are 2 of the major ones, right? Under climate change, under those climate change projections. And then what we do is if we bring in all of the projections, you can see that those 2 extremes bracket, the MC2 projections using all GCMs and RCPs. So what I'm going to do now in future slides is I'm just going to show you one set of scenarios where essentially each Monte Carlo that we ran in the model sampled from a different GCM, and that GCM would be used for that entire realization of the model. And we use the external variable for each iteration. We would randomly sample from one of the GCMs. And that sampling of the GCMs would then drive a number of things. It would drive productivity. over time, and it would also drive when the drought transition multipliers, the amount of drought that's occurring on the landscape over time as well. So, and there's, something that bugs me a little bit about this graph is the blue line is kind of the current climate and the productivity. And I feel like the MC2 projections early on, they're still kind of reflecting the maximum possible variability in productivity, but it's a little bit strange that right away, the productivity projections for some of the GCMs get to be very low. So, again, this kind of illustrates the need to look at other possible approaches for making productivity projections. So the next thing I'm going to talk about is bringing in grazing. And here in this diagram, I'm just showing the blue arrows now are just showing the grazing transitions. So the grazing transition, some of them you see the little circles, that means implies no change. And some of them imply change, like transitions, a lot of transitions to annual grass, a lot of transitions to mesquite. And so usually those are specified with proportions. So essentially, I think what the ILAP modelers were saying is when a particular site gets grazed, there's some chance that you would undergo a state transition. So not every time grazing occurs. But you might imagine that the more grazing we add to this landscape, the more chances that you would eventually see some kind of a state transition. How am I doing for time?
15 minutes.
I've
got 10 minutes left.
10 minutes left. Okay, great. So the way we impose grazing on this landscape is we actually determined, okay, well, how much does an individual animal need to eat? We had productivity. So whenever a grazing transition occurred on the landscape, we essentially assigned a value of, and I can't remember the exact percentage, but in the guidance for range management, there's typically a sort of a certain proportion of the productivity that's recommended that you take from a site. So when we assign grazing transitions to a site, there's an equivalent transition attribute that says when you graze a site, the animal is eating X percentage of that year's productivity. So we use state attributes for that. You might be familiar for that. And then we're able to use state attribute targets where we tell the model where we want for every year in this landscape, we want to apply 100 animal unit months of grazing per year to this study area. And so you can see that we're maintaining a relatively constant amount of grazing with that target, 150 animal units months per year, but the amount of area that's actually being grazed is varying. And the reason for that is on years when there's very high productivity, you don't need as much area grazed to achieve that amount of animal unit months per year. And in animals where productivity is very low, you got to graze a much larger area. Okay. So now this is with the current climate scenario and the low productivity threshold for drought. Okay, now this is bringing in one of the climate projections, and I'm just showing you one climate projection because otherwise the noise is so high that you can't really see what's going on. But you'll notice that with this climate projection for the BCC GCM with the low productivity threshold, first of all, there's some years where you can't achieve your grazing target. So there's just not enough land out there that's grazable that you can achieve your grazing target. And the other thing is there's some years when you're grazing much larger areas in order to try to achieve your grazing target. And so that would mean as you graze larger areas, there's more chances that those transitions that drive phase changes are going to occur. So this slide kind of tries to illustrate what is the risk of, even though you're trying to graze 150 animal unit months per year, that there's not going to be enough food out there for the animals that you want to put on that landscape. And so the blue scenario represents current climate, and the red scenario represents the future climate, the full variability of all the GCMs and RCP. And what you see on the x-axis is how far below your target you are, and on the y-axis, how frequently does that happen? So first of all, you can see, and here's the averages. So on average, there's a higher, you're coming in on average each year 8% or 7% below target, whereas under climate, you're getting pretty close to your target each year. And then there's also this long tail where there's some years where there's a risk that you actually come way below your target, amount of animals that you can put on that landscape. In terms of the impact of grazing on composition of vegetation, so if we look at current climate, the blue scenario is current climate, and the red one is current climate if we add grazing. When we add grazing, we see some big composition changes under current climate. We see, an increase in the sparse grass, a decrease in the perennial, where's the perennial grass? Here, so a big decrease in the perennial grass. This is one of the most dominant ones. So as we add grazing, we start to see more of those grazing transitions. And then, and I'm just highlighting these boxes because these are kind of the most dominant on the landscape or have the largest areas on the landscape. Now, bringing in climate, one of the interesting things is that once we add climate, there's differences between current climate and the future climate projections, but the differences on whether there's grazing or not, the differences on whether there's, got 5 minutes left. The differences on whether there's grazing or not tend to disappear. So under climate change, it seems like the drought effect on vegetation is overwhelming the grazing effect on vegetation. Okay, and I just put this up not to focus specifically on the, I don't have a message to say about these particular maps, but just to say that these were spatially explicit simulations. So, we could, just like Colin, we haven't done this, but just like Colin showed the probability of being in a particular state. In future, we could show projections of, under each scenario, the probability of being in a particular vegetation state, or the probability, I think this one's an example of probability of annual grazing probability. So there's certain parts of the landscape which for some reason are getting more grazing than other parts of the landscape. And so in terms of the implications for rangelands in this region, as the productivity becomes more variable, there's an increase in risk that you might not achieve the grazing targets that you want to achieve. And so there's that potential increase in risk driven by climate change. We haven't really explored, I'd like to do a sensitivity. Well, first of all, I'd like to extend this to a much larger area because this is kind of a very small area. But I'd like to explore, a sensitivity analysis to your grazing targets. As you reduce your grazing targets, how does that lower your risk of achieving it? In terms of vegetation composition, we saw that if we have current climate and we add grazing, there's going to be a change in vegetation composition, or that we're projecting change in vegetation composition with these models. Under projected climate, there would be a different outcome versus the current climate variability. But with projected climate, grazing didn't seem to make such a big difference because the drought effect on vegetation composition is overwhelming the grazing effect. And so, I'm really interested in trying different methods for the productivity projections because of those issues I highlighted with MC2. Trying to come up with maybe some more support for what should the threshold be for those drought transitions. Looking at the uncertainty that we have in the landscape composition and also working with a much larger spatial extent.